mentioned Nader Sihadbak, who I was talking about, the guy who's like teaching computer architecture classes.
Yes.
He could be one of the guys who can actually be one of the three people, because the thing is, of those three people, they require two to be CS, and then one can be from any other department or could be CS. So I can have him as the
Then you go get him if you
so
can.
I can
Okay.
have him as the third guy. I just can't have him as my primary PI because they need someone from the CS
Right.
department. That's
Yeah.
cool.
Okay. Sounds too complicated. Okay.
I don't make the rules. The department makes the rules, right?
Okay.
So it is what it is.
Fair enough. Okay. Sure. It's not connecting. And this is not on either. That one's working, yes. Good. We're going to all huddle around this thing.
Oh, does this one still not work?
I don't see it. Yes.
Did you HDMI it?
Yeah.
Okay.
But there's usually another plug on this thing. This is working, yes. Can I move it? Yeah, yeah. Good. Excellent. And is the recording on? Oh, okay. Great. Testing, 1, 2. Testing. Great. Okay, so let's begin. Today's lecture 17. There are only 3 more lectures to go. There's no lecture this Wednesday, as you know. Then next week there's a Monday and a Wednesday. And the following Monday, namely 2 weeks from today, is the final. I issued a new homework last night, due next Sunday. And I may send in 1 or 2 more homework assignments, even with shorter periods, because I want to get some of the GMM and the GG1 in homework. The one I assigned last night was basically the MG1. Okay, so we're going to have to move rather quickly. I noticed only 11 people handed in the assignment that was due last night. Counting those other 3, that'd be 14, but there's usually 3 more that come in. I don't know who's delinquent, but if any of your friends are delinquent, how will they send them in so that they get marked then? Email to you, okay. Yes. I'm sorry, excuse me? Help me at the break to make that happen.
Like it was due yesterday, right?
Yes.
It'll basically say due March 3rd and late due like March 6th, whatever you said. So like people can still submit until March 6th, but it'll be marked as late.
Great, so we'll work that out at the break, so I can enable that, right. You can teach me how to use this darn system. Okay.
From your point of view, but I know like from the student side, there's a way, like you do,
Yeah, okay, you guys know. Good. So let's do a review, a very quick review. Last time we did MG1 quickly. MG1, of course, is Poisson arrivals, exponential to arrival time, arbitrary service time with rho less than 1. And we went through the derivation of the 6 key equations, the 3 Pollaczek-Khinchin mean value formulas for average number, average time in system, average time in Q, and then went to the transform of the distributions, again, the Pollaczek-Khinchin transform equations. Basically, this is the Z transform of the distribution of number in system, distribution of time in system, distribution of time in Q. And that was basically what we did. It's a very nice set of analytical tools. So today, we have a whole new topic to cover, and it's the Q, G, M, and you might expect me to put a 1 after that, but the GMM system is no more complicated than GM1 by and large. So we're going to go jump right into it to the GMM. Notice we did not do MGM, multiple server. That's much harder. This particular system is a lot easier than the MGM. So that's our goal today. Okay, so just to remind you, in this case, A of t, the inter-arrival time distribution, is arbitrary and has a mean inter-arrival time of 1 over lambda, same notation. But the service time density is exponential. It's mu e to the minus mu x. And I say GMM is almost as easy as GM1, so we'll do it. And we're going to assume that the average service time is such that rho is equal to, well, if there's m servers, how fast can the system discharge work? How many seconds of work can the systems do in 1 second? One of them uses the amount of service per customer, but you got a server there generating seconds of work. How many seconds of work can one server do in 1 second? 1. So how many can M do in 1 second? M. Okay? Now how much work is coming in? How many seconds of work are coming in per second? Well, there's lambda customers per second coming in, and each one brings how much work? X bar. So lambda x bar is the amount of seconds coming in, and the rate at which can be pumped out is m. So this is the definition of rho in this case. And of course, x bar is equal to 1 over mu because of the exponential choice. Okay, so let's think about that. How are we going to solve this? What do we need to know to predict the future? Well, for one thing, we can take the simple approach and say we need a 2-dimensional state description, namely the number in system. In order to predict how many there are in the future, what else should I know? At an arbitrary point in time, what's the state description at an arbitrary point in time? How many there in the system, n of t, and what else? What else has memory in this system?
How much time the arriving customers spend in the arrival space?
How long since the last customer? Because the inter-arrival time density changes according to how long it's been since the last arrival. So there is memory. Okay. So we can make that a 2-dimensional, okay? So number in system and time since last arrival. But it's a nasty 2-dimensional description. And so we're going to choose to use, and by the way, if we use this, this would basically lead to what I called before as the method of supplementary variables. There's 2 variables here. But there's an easier way. There is what we'd like, which is the method of the embedded Markov chain. Are there any points in time where I don't have to keep track of how long it's been since the last arrival? Namely, I know it. Yes, John? Yeah, when a customer arrives, the time since the last arrival is 0. So let's think about those as the embedded Markov chain point, because just give me the number and system of those points, and I can go on, as we did with MG1. So let's think about that. So let's draw the picture now. Let's draw our usual picture of server and queue. And let's watch a particular customer come in. Let's watch CN arrive. Say he comes in right here. And let's assume the next customer comes in at some point later, say here. And that's going to be customer CN plus 1. No other customers come in between them. They're numbered, n, then n plus 1. However, this customer, some customers are going to start going into service at some point in time. Oops, I want to make that black, I'm sorry. So here's the customer. And that whoever this next customer is that I just drew in black must have gone in when what else happened? If he goes into the server, what must have happened? Yes? A customer must have left. So somebody's leaving here. And that's going to happen a number of times. I'm going to put some dots here. And here's another one such, say. And then after that, we'll see other things happening. There'll be another customer going in here when a departure occurs. And let's assume at some point goes into service when some other customer left. Okay. And time is marching out this way. Now, when CN comes in, he finds so many in the system, and that's the embedded point I'm after. So let's identify that point. Let's draw that actually in blue. Let's assume that he found Qn, I'm going to call it Qn prime, found. In MG1, we call it Qn as a number that a departure left behind. Here we say how many are found. So I'm calling it Qn prime. So that's what's going on here. And the next such Q I need is right here. When the next guy leaves, Qn plus 1 are found. Namely, Qn is the number found by customer n. And again, this is the next embedded point. And we want to study those points because they're going to give us the answers we need, as you'll see. Okay, so let's put down some notation now. I'm going to define formally now. Let Q sub n prime be the number of customers found upon arrival of Cn. Found by Cn upon arrival. Now, of course, during that interval, some number of customers left. And I'm going to draw that this way. That group is the group of customers that left during the inter-arrival time. I'm going to call that, no surprise, V sub n plus 1, but prime because it's a little different from the MG case. So let me define that down here. V sub n plus 1 prime equals number of customers served between arrival of Cn and Cn plus 1. Now this begins to look almost like the dual of the MG1 system. I'm looking for how many were found by an arrival instead of the number left by a departure. I'm looking at the number that arrived during departures instead of the number that arrived during a service. So the duality between service and arrival is pretty clear. If you look back to your other notes, you'll see that. Okay, so the big deal is, how do I write down what Qn plus 1 is? Qn plus 1 prime. I want to write it in terms of Qn. Well, let's see. The number that are found by the next guy is the number that were found by the previous guy, Qn, plus Cn himself, less what? Exactly. Vn plus 1 prime. So let me say that again. How many the next guy basically finds upon his arrival depends on how much the last guy find. Then that last guy came in, that's one more. But of that group, some left. How many left? Vn plus 1. So that's what the next guy finds. It's very logical. But now we got to play with it. And I'm going to define the transition probabilities, Pij, between the various states as follows. It's the probability that the next guy finds J, namely Qn plus 1 prime equals J, given Qn prime equals I. And these are the transition probabilities in a transition probability matrix that I'm going to use. Now we can say something else also, that Pij is the probability that a certain number of customers are served during an inter-arrival time. So how many are served during an inter-arrival time? Okay? Namely, what is that number? Well, put the V on the opposite side of the equation. It's a number found. It's basically what the first guy found. The previous guy stayed I. I were there, plus him, minus what the next guy finds, namely minus G. That's how many basically are served during an inter-arrival time. Namely, I know I'm starting off with I and ending up with J. Okay? So I got to make sure that this many was served. The minus J means you left the other J for me to find this next arrival. Of the I plus 1 that the last guy plus him found, he's got to leave me J. So all the rest have to leave. So him plus the number he found minus how much he's going to leave is that many got served. Okay. And we're going to be playing games like that. I want you to try to get that in your head. It's a little tricky. Now we also know something, that Pij is equal to 0 if J is greater than I plus 1. The next guy can't find more than the last guy found plus the guy himself. Things are only leaving after the next guy arrived. He plus the number he found is I plus 1. So this guy can't find more than that. In fact, how can j equal I plus 1? What has to happen? Yes? Opposite. Nobody gets served. Guy comes in, finds I plus 1, it's him. Next guy finds the same amount, nobody left. You're not counting the second guy. He's not counting himself. Okay. Okay. So let's look at a state transition diagram now. And only out of state EJ remember, EJ is a state when there are J in the system. Let's use it I, I'm sorry. State I, sorry. So here we draw state I, and there's an I plus 1, and there's an I plus 2, and below that is an I minus 1, an I minus 2, dot, 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 down to a state 1 and a state 0. And on up. Okay, I'm in state I. Can I go from state I to state I? Sure I can, okay? And let's call that, according to the PIJs, that's simply PII. Whoops, wrong state. That's simply PII. That's not telling me anything new. And to go up 1, yes, I can do that as well. That's PI, comma, I plus 1. Can I go from I to I plus 2? No, why not? Right, only people are leaving between these two arrivals. So what the previous guy found, we said this before, previous guy found, plus what that guy himself, is all that's in the system when the next guy comes in, if nobody leaves. Okay, but we can go down, and the obvious transitions here are PI, comma, I minus 1, and down to here, and down to here, and finally down to state 0. State 0 is just PI 0. Notation says it all. Okay. And as I told you, it's ergodic if rho, which equals lambda over mu, is less than 1. Okay, now there's some definition of what we're after. We've already defined this. Let R sub k equal the limiting probability as n goes to infinity, namely the equilibrium probability of the probability that number found by Cn, namely Qn prime, is equal to k. Remember, Rk described what the arrivals see. Dk described what the departures see. And pk describe what happens at all points in time. Okay. Now, if you're given capital P, which is the matrix of Pij, the transition probability matrix, then how are you going to find R? Well, let me define the vector R vector as R0, R1, etc. You find that vector R by what equation? R equals RP. Just as always. With one more equation, of course, the summation of all the probabilities goes to 1. So that's the setup. That's our job. Okay? In order to move ahead, we need to do two things now. One, what are the PIJs? And then secondly, once I got that, to solve this R equals RP equation. So there's nothing new about that. Tell me what the transition probabilities are, plug it into R equals RP, solve R equals RP, and you're done. And by the way, if I gave you capital P, and you were about to solve R equals RP, what's one way to do it? What's the aggressive way to do it? Namely, guess the solution. And if it satisfies that vector R equals RP, you're done, because there's a unique solution for these ergodic Markov chains. And we're going to do a half guess as we move along, okay? Okay, so let's consider the range of I and J. And I'm going to copy a picture, but they're going to draw it for you because you have to draw it as well. Oops. Come on, I want to copy you. Maybe I've got to do that. Yep. Thank you, good notes. We're going to try to draw this picture, which is the IJ plane. And as you see from this picture, it's broken into 4 regions. We're going to draw those regions right now, okay? So I'm going to, this is where we're heading. I'll shrink this a little bit. But let's draw it so you see what's going on here. Okay. The horizontal axis is I, integers, and the vertical axis is J. And it goes from 0, 1, 2, 3, 4, etc. Now I'm going to break this into 4 regions. First region is going to be the following. It's going to be the region I mentioned before where all the Pij's are 0. Namely, you can't have more than one found by the next guy than the previous guy found. So let's draw that. And well, let me draw some dots here first. It's a little easier. These dots I'm drawing are the various Pij's whose values we have to find. Okay. I'm going to draw a diagonal right up through here. I'm going to call this region 1. In region 1, we're going to start to calculate its values down here. Is the case for which J greater than I plus 1. And we know already that Pij is equal to 0 in that region. So we're done with that region, if I drew it carefully. And I want to make sure that, for example, if the last guy found 0, then the next guy can't find more than 1. He can find 1, but he can't find 2, etc. He can't find these values up here. So let's look at the region 2 now. Region 2 is for the following region. J less than or equal to I plus 1 less than or equal to m, the number of servers. Namely, no customers are waiting. And all present have their own server. So everybody's in service during the whole period here in the I to J. Now remember, during this inter-arrival time, which is the interval we're looking at from I to J, I plus 1 minus J will complete service. And the probability that any customer, any particular customer, completes service within the t seconds of inter-arrival time, or any t, is what? Well, it's exponential service. A whole bunch of people in service, each going exponentially. So the probability anyone completes is 1 minus e to the minus mu t. And the probability that a customer does not depart in this interval is the other piece of that is e to the minus mu t, once you're given t. So what do we get? We get the probability that I plus 1 minus j departures in t seconds after Cn arrives, namely counting the inter-arrival time, given, so I'm going to put the word given here, that he found, Qn plus 1 found I, can be found as the following. So of the I plus 1 that are in service now, we only want I plus 1 minus j to be selected to go. So I'm going to do a combination. That's equal to I plus 1 choose I plus 1 minus j, combinatorial. And then of that group, I've already decided how long it takes each. Of the I plus 1 minus j that gets served, each one takes 1 minus probability 1 e to the minus mu t to the I plus 1 minus j. And the rest don't get served, so it's e to the minus mu t, all of that to the j. They remain. And of course, the binomial coefficient, just to remind you, is also equal to I plus 1 choose j. Let me write that more clearly. It's a little sloppy. Oops. That's I plus 1 choose j. And we know that n choose k is just n factorial over k factorial and minus k factorial. Okay. So now we want to basically remove the condition on t. On how long the inter-arrival time is. And that'll give us Pij for this range. So removing the condition, we're going to integrate over all values of t from 0 to infinity. And way at the end here, we're going to put down the probability of a particular t, which is little a of t dt. And inside, we're going to put the thing we just cooked up as the probability of this happening, namely I plus 1j. And this first factor 1 minus e to the minus mu t, all of that to the I plus 1 minus j, times e to the minus mu tj. And again, to remind you of the range, it's j less than equal to I plus 1, less than equal to m, all customers always being served. So that's the answer. That's what the Pij is in region 2. In the region 2, I should identify here, as you go out to m, let's assume m is right here. We're going to go right up here. I'll do this in red. This is region 2. So we just found the Pij's in that region. It's that equation. Once you know A of t, you can plug it in. So this is region 2. Now let's go to region 3. Now in this region, we're going to consider the following range. It's m less than equal to j, of course, less than equal to I plus 1. Which is also the case for I greater than equal to m, of course. If the first part is true, the second part is true. Namely, all m servers are busy throughout the inter-arrival time. Throughout the inter-arrival time. It wasn't true in question 2. In question 2, you had a number times when the servers were all busy, and then when some were not. In fact, you always, all the customers had a server of their own. Doesn't mean all them servers were busy. So in this case, basically, if all them servers are busy here and they're pumping people out, okay, it's a pure Poisson death process. They're killing people. They're leaving. At what rate? M mu. So let's say that. So it's a pure Poisson death process. All the servers are busy with parameter mu. Now a little notation. I want to denote by the following phrase, namely, quote, T, comma, all m busy. By that quote, I mean all m servers are busy, pretty obvious. During the interval t. So let's make some calculation now. The probability that k customers are served given that phrase over an interval t and all m servers are busy, all m busy, is going to be what? Well, that's our death process, right? So given that they're dying at a rate mu, what's the probability that k of them die in an interval t? Okay, that's just our usual calculation. So it's mu t to the k over k factorial e to the minus mu t. Now remember, that I plus 1 minus j must be served in t seconds if we're going from I to j. So let's write down that Pij. In the region, it's region 3 now, it's the following. It's the integral, 0 to infinity, of what? Over all possible interarrival times. I'm going to put that out here. And here I've got to put down the probability that I just described that k customers are served given t and m. So it's m mu t. But to how many? How many need to be served? What's the k I'm looking for? Well, I just told you in the line above, I plus 1 minus j have to be served. So the exponent here for k, 2 lines above, is just I plus 1 minus j. Same thing for the k factorial. It's I plus 1 minus j factorial. And then e to the minus m u t times a of t dt. But notice in this expression I just wrote down, I and j don't appear independently. They always appear as I plus 1 minus j. Let's make a substitution, okay? So I want to define a quantity beta sub I plus 1 minus j as this p ij I'm after. In the range, remember, m less than equal to j less than equal to I plus 1. That's the region 3 we're talking about. And of course, that means I is greater than or equal to m. But beta sub n is simply the probability that n customers get served in an interarrival time given that all m are busy. So beta sub n is equal to p sub I, comma, let me make a substitution first. I'll make this easier for you. Let's denote n as this strange combination I plus 1 minus j. Which means that j equals I plus 1 minus n. And so beta sub n is equal to the probability of going from I to I plus 1 minus n. Namely, n is the number served. Okay? And that's equal to the thing we just cooked up, is the integral from 0 to infinity of the m mu t, and now replaced I plus 1 minus j by n over n factorial e to the minus m mu t a of t dt. And again, that's in the region 0 less than equal to n less than equal to I plus 1 minus n minus m. So that's the region 3. That's the equation that'll give us the Pij there. Okay. Remember, Pij, we just said, is this beta function. And we just found it. So let's go to region 4 now. Oh, let me draw region 3 for you, by the way. Region 3, by the way, is the good region when all the servers are busy. Let me draw that back up here. It's drawn correctly in the book, in the picture I showed you. Let's see now. That means that m is right here. The region I want is just below m, going out here. And this is the region 3 is above that then. Whoops. That's the region 3. And there's a remaining region 4 down here. Yes. J is what the next guy finds. You're going from state I, when Cn arrives, he finds I in the system. Cn plus 1 finds J. And so the transition probabilities are going from a state at the last arrival to the next arrival. I here, J here. Okay, J is how many the next guy finds. What's the most he can find? How many the last guy found plus the last guy, and that's it. So it's I plus 1. But not possible, right. And this is the region 4. So let's talk about that down here. And this is for the following range. J less than M less than I plus 1. Basically, Cn arrives to find M in service and I minus M in the queue. So some are in service, some in the queue. And things happen, okay? Now we can go through the calculation, but I'm not going to do it. This is exercise, which I did not assign to you, by the way, out of mercy, okay? This is exercise 6.1 in the book. But you might want to look at it. I don't want to take the time now to derive it. It's not that hard, by the way. But it turns out to be a nasty little equation. And here it is. The expression finally is Pij is equal to the integral from 0 to infinity over the interarrival times of M choose J. Basically, you got to wait until the queue empties. While the queue is empty and people are leaving at what rate? M mu. And then when the queue empties and not all the servers are busy, the departure rate is shrinking. So you got sort of two regions you got to deal with. That's why the equation is a little complicated. The important region is region 3, as you'll see. So the final answer is here. It's e to the minus mu tj times the following big bracket, integral from 0 to t, m mu y to the I minus 1 over I minus m factorial times the following combination, e to the minus mu y minus e to the minus mu t. That whole thing raised to the m minus j power, close bracket, and then we finish with the a of t dt. I left out, I'm sorry, there's an m mu y before the bracket. Sorry about that. In fact, let me steal some space, which, again, you can't do so easily, but I can. Times m mu y, this is the inner integration. And the t, the y is the inner, and the t is the outer. Okay. I never said it would be easy. Yes, question mark.
So, conceptually, would it be correct to understand region 2 as when you come in, when Cn comes in, there are some idle servers, and then when Cn plus 1 comes, there's still some idle servers?
Let me recall for my... Yes. In fact, there's always... Well, as soon as the first guy comes in, he can fill the servers up. But there's nobody in queue. That's the point. That's what happens there. So nobody in Q means either all or some of the servers are busy. But there's nobody beyond M. Notice, the number of people is less than M. And that's what this picture showed you here, you see. In region 2, I sees less than M. Okay? Okay. The point is, this is a nuisance to go after, these PIJs. I'm just showing you there are ways to calculate. I calculated 3 of the 4 regions for you. You can do as an exercise. Never said it would be simple. But basically what we have now, before we take the break, is we filled out the PIJ, and I'm going to pull it up here now. This is what the PIJ matrix looks like. And by the way, it's rotated. The I and the J is switched here. Okay? I is going up and J is going horizontal. So you see that region 1, where you had a bunch of zeros, is right here. The region that I like is basically this region here, where the betas take over. Because that's going to determine the equilibrium behavior. Okay, so let's take our break. And our next job, having found out what capital P is, what's our next job? To find the RKs from what equation? What's the vector equation? R equals RP. Fairly straightforward. We'll do that right after the break. Let's take the break. Come back at 3, please. Yes, right. Yeah. Okay. So now that we have capital P, it looks like this. We're going to go after the equation R equals RP. That lovely picture just went away. Let me find it again. Okay, so we know this probability transition matrix, and so the question now is we need to solve R equals RP. Let's begin by finding some results along the way. Namely, I want to start off by finding the conditional distribution of the Q size. I really want the unconditional distribution of Q size. By the way, the condition is that the Q doesn't empty. You'll see in a moment. But let's find the conditional. That's a little bit easier. And this gets a bit convoluted, as we see. So remember what Q sub n prime is. It's a number found by Cn, and Vn plus 1 is the number that arrived between the arrival of Cn and Cn plus 1. And we had the equation Qn plus 1 prime equals Qn prime plus 1 minus Vn plus 1 prime. And we're looking for R sub k, which I told you is the limit of the probability of these things, probability that Qn prime equals k as n goes to infinity. And R is, I need vector signifies here, it's a vector R into the matrix P. Now, as I said, we could guess the solution, and we're going to do a little bit of guessing soon, but let's start with some intuitive arguments to see where this takes us. So, when we're all done, if we show you a solution that satisfies those equations, you can't argue with it, but let's try to motivate it, okay? So I'm going to make a definition now, something we've seen before. Let n sub k of t be the number of arrival instants in the interval 0 to t in which the arriving customer finds a system in state K. But something happens at time 0 given 0 customs at time 0. That's an initial condition, but we don't really care because we're going to let time run to infinity. Okay, but This has to be a precise definition, and there it is. Okay? Now, notice, the system can move up by at most one state but down many. That was the picture we saw before. In any single transition. What's a transition? Between two arrivals. Arrival 1, next arrival comes, that's a transition. So a picture similar to what we saw before. We had k, we had k plus 1, we have k minus 1, etc. I'm using k now as a system state. And the states go, either you can come back to this own state, you can go up by 1, you can go down by 1, and down a whole bunch more. Okay? Now, for m minus 1 less than or equal to k, I'm going to make a definition. Namely, we have it basically in a state where there's all but one, at least all but one server busy. We're going to let the notation sigma sub k be the expected number of times state ek plus 1 is reached between two visits to ek. So from k, if I go to k plus 1, how many times do I hit k plus 1 before I come back to k? And by the way, notice a little thing here. If I'm going to leave k and later on leave k plus 1 somehow, if I come down here, for sure, I got to hit k before I hit k plus 1 again. So talking about k is the same as talking about any state to its left. We're going to take advantage of that in just a moment. Okay. Now let's start to make some calculations. Note the probability that you visit this ek plus 1 0 times between a visit to ek, 0 times between visit to ek plus 1. Is how much? Remember, beta 0 is where you go. It's 1 minus beta 0. Namely, if you serve at least one customer when you're in state k, you're going to hit state k again before you go to k plus 1. So you leave k. You don't visit ek plus 1, which means you had to serve at least one person. And by the way, this is not k plus 1 here. This was a k, I'm sorry. In other words, you're in ek. What's the probability you don't hit ek plus 1 before you come to k again? Okay? The only way you can hit k plus 1 before you come to k is to serve nobody. This is the probability you serve at least 1. So that's the probability you're going to visit 0 times, okay? And let me remind you what beta n is. Beta n is the probability you serve n during an interarrival time. With a condition given all m busy during this interval. And by the way, that's why I put the condition at the top of the page, k greater than or equal to m minus 1. Okay. Another way to say that is the following. That is, given you an ek, the only way to reach k plus 1 before another visit to ek, I said this a moment ago, is for no customers preserved. And that's the probability beta 0. Okay. Okay, now I want to introduce another variable. The variable is gamma. And gamma is going to be the probability you leave ek plus 1 and return to it without passing through ej. For any j less than or equal to k. And using the argument I gave you before, if you hit any j less than or equal to k, you're going to hit k before you come back to k plus 1. Okay? So that's the probability that you leave ek plus 1 and return to it without passing through ek. Now, interestingly, gamma is independent of k. In the range where all the servers are busy, where k greater than or equal to m minus 1. Since all the m servers are busy, doesn't matter how many are busy, but it doesn't matter how many other people there are, you still got the same number being popped out. Okay? So the probability of n occurrences, now I can put some calculation here, n occurrences of state ek plus 1 between two successive visits to ek is equal to what? Well, first of all, you got to be sure you get into k plus 1. So you got to have for the first transition, nobody gets served. And then you need gamma n minus 1 more, where you serve at least 1, and then a 1 minus gamma to make sure you come back down. So you want n occurrence to be k plus 1. If you look at the picture up here, I'll use my funny pen. You're in k. You got to get to k plus 1 first, okay? And then you've got to basically stay up here before you fall down here. And the gamma is the probability you stay up there. How many times? N minus 1, okay? You hit k plus 1 once. N minus 1 more, that's n, and then you fall down. So you've done exactly n in k plus 1, which is exactly what this probability says. It says right here, you want n occurrences of this state before you hit ek again. Okay, so that's fairly straightforward. Okay. Now let's recall what sigma k is again. Recall sigma k is the expected number of times to visit ek plus 1. Expected value of number of times to visit ek plus 1 between visits to ek. So now I want the expected number of those operations. Sigma sub k, by definition of expectation, is the sum over all possible values of n, from 1 to infinity, of n times the thing I just cooked up, the probability, namely beta 0, gamma to the n minus 1, 1 minus sigma. And if you can't figure that out, leave this classroom now. Okay, not by inspection, but you have to be able to do it. What's the trick you're going to use to form that sum? Partial derivative with respect to gamma. You got n sigma to the n minus 1. Okay, so you do it. Okay, and that turns out to be beta 0 over 1 minus gamma. Okay. And that's again for the range k, whoops, k greater than or equal to m minus 1. And notice that sigma k is independent of k. Okay. So let's define sigma itself to be defined as sigma sub k doesn't depend upon k. And that average is beta 0 over 1 minus sigma, 1 minus gamma. Now, by definition, and here's where the intuition comes in, sigma, okay, it's the number of times you hit k plus 1 per time you hit k. So that in some sense, intuitive sense, is the limit as t goes to infinity of the number of times you're in k plus 1 over the number of times you're in k. Any of the physicists or engineers in this room feel that's intuitively correct. And in fact, it is. Okay, so let's continue that. So sigma, which is equal to, because it's the limit of that thing, what's the limit of the numerator of the denominator? What is the limit of the numerator? Number of times in ek plus 1, number of times in ek, that's just the ratio of r sub k plus 1 over r sub k. Again, this is in the range k greater than or equal to m minus 1. So look how nicely we've come up with this expectation, okay? I mean, number of times in ek plus 1 goes to infinity, so does ek, but the ratio is the ratio of the probability of finding, of a new arrival finding k plus 1 in the system versus k. So we're using some intuition to try to derive our guess, if you will. So rk plus 1 is equal to sigma rk and again, same range, k greater than or equal to m minus 1. So let's use this recursively. That means r sub k plus 1, my family keeps calling me here, is equal to sigma times rk, but rk is what? It's sigma rk minus 1, which then is sigma times sigma rk minus 2, dot, dot, dot. And so we get that r sub k is equal to sigma, excuse me, some constant k times sigma to the k. There's sigma of these terms. There's k of these terms. Again, k greater than or equal to m minus 1. Well, that's interesting. In this attempt we're after, what are we going after? R equals rp. I've already determined what the tail of that r vector looks like. For k greater than m minus 1, it's of this form. It's geometric. Interesting. So let's say that. I.e., the distribution of number of customers found by an arrival is geometric for k greater than or equal to m minus 1 and this is true for all GMM systems. I'm going to make that point stronger in just a moment. And by the way, this can be proven rigorously by renewal theory. We've taken steps around that. Renewal theory talks about these limits we discussed up above. Okay. And we could have guessed that if we wanted, and now that we're so small, we can guess. Question? No, that's an unknown constant. It's proportionality. We're going to have to find it. That capital K is just a constant that has to be solved for. So that means we could have guessed the following, that this vector r is equal to the following. Some unknown number r0, r1, out to r sub m minus 2, but then it's what we figured out. It's k sigma to the m minus 1. That's what k is, little k. And k sigma to the m, k sigma to the m plus 1, comma, dot, 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 out to infinity. And I'm going to label this equation as, whoops, red star. Now, to prove the correctness of this guess, in some sense we're guessing it, we've got to prove it's correct, okay? So what do you do to prove it? You plug it into the r equals rp equation, okay? So let's say that. To prove correctness of this guess, if you will, this intuitively generated guess. Let's plug it in. The kth equation for R equals RP for the range k greater than or equal to M. Let's do that. That means R sub k is equal to, we presume, is k sigma to the k. And if you look at the equation, that's a summation from I equals 0 to infinity of R sub I pik. That's what we mean by R equals RP. And that's equal to the summation I equals k minus 1 to infinity of R sub I pik. Why? Why? You're not listening. Why did I change the lower index from 0 to k minus 1? You asked about that a moment ago. Let him answer. You! I've thrown away all the terms from 0 to k minus 2. Right. You can't have more there than came in. So let's point that out. Pij equals 0 for I plus 1 less than j. That's region 1, if you will. Okay. Now, but we're focusing in region 3 now. Remember that region, whoops. And I'll write this in red so you remember. Region 3 showed us the following. That P I, comma, I plus 1 minus n, which we call beta sub n, is equal to the rather simple formula, integral from 0 to infinity, mu t to the n over n factorial e to the minus mu t a of t dt. Remember, this is when all the servers were busy. So I want to consider k as follows. So consider k equal to I plus 1 minus n, or if you will, n equals I plus 1 minus k. And so beta sub n is equal to the new subscript, beta sub I plus 1 minus k. I picked that up from what I just showed n is. That's a k. Whoops. And that's equal to p sub ik. So we get this thing I cooked up at the top of the page, that limiting sum from I equals k minus 1 to infinity of Ri pik is equal, we're going to plug in now, summation over the same range, I equals k minus 1 to infinity of R sub I, and I know the pik, I just put it up there before, that's beta sub I plus 1 minus k. So this Rk that I'm claiming is equal to k sigma to the k. If you look at the top of the page, that's what I said. It's equal to the sum from I equals k minus 1 to infinity of the Ri on the right-hand side now, which is k sigma to the I, times the beta term, beta sub I plus 1 minus k. Now to divide this whole thing by k sigma to the k minus 1, capital K, by capital K sigma to little k minus 1. And what do we get? We get that sigma on the left-hand side is equal to the summation I equals k minus 1 to infinity of sigma to the I plus 1 minus k times the beta I plus 1 minus k. Well, this is begging for a change of variable again. So change variable. Again, n equals that funny thing, I plus 1 minus k. No surprise, we've used that before. And we know beta sub n from region 3. So let's write out what that is. Whoops. That says that sigma equals summation n equals 0, we change variables to infinity, of sigma to the n beta sub n, and plugging in what the beta n is from the solution for 3, which we derived. So we get left-hand side sigma is equal to the summation n equals 0 to infinity of sigma to the n times beta sub n. And beta sub n is that integral I gave you a moment ago. Integral from t equals 0 to infinity of the quantity m mu t to the n over n factorial e to the minus m mu t times a of t dt. And no surprise, that's equal to the exchanging integral and summation, integral from 0 to infinity on t of e to the minus quantity m mu minus m mu sigma, all of that times t, a of t dt. What did I do? I saw that the summation is an exponential, our good old exponential series. So what does this last thing tell me? That tells me that sigma is equal to this last integral I see, that's a Laplace transform of little a at that funny term inside the parenthesis. So that's a star, we've done this so many times, of mu minus mu sigma. And that is a very nice equation. This equation must be satisfied if our assumed solution is correct. And it's a functional equation for sigma. And we can show the following. If our friend rho is less than 1, so it's ergodic, then there exists a unique real sigma in the range 0 less than sigma, strictly less than 1. A solution to that equation in red. By the way, in parenthesis, sigma equals 1 is always a solution. We've seen this kind of thing before, but that's not the one we want. We want it in the range 0 less than sigma less than 1. Okay. But we still have some unknowns. I mean, this gives us the number sigma, which appears in our assumed solution right here. That tells us what the sigma is. And remember, that, what do we need now to get all of R? We got the sigmas. What are we missing? We're missing K, and we're missing these initial terms. Never said it was easy, but the results will be very nice. Okay? Okay. But before we do that, let's exploit what we now know. So let me say before we find K and R0, comma, R1, comma, out to R sub m minus 2, let's exploit what we just found. Namely, let's exploit the fact that R sub k equals k sigma to the k for k greater than or equal to m minus 1. Because we know sigma by that functional equation. So let's ask a couple of questions. Let's ask ourselves, let's calculate the probability that an arrival has to Q. Well, what is that? That's the probability that he finds at least m in the system. That's the sum from k equals m to infinity of rk, and we know rk there, so that's the summation, k equals m to infinity of capital K sigma to the k. And of course that, by a simple geometric summation, is capital K sigma to the m, the first missing term, the first term minus the first missing term, the other missing terms, over 1 minus sigma. And again, we know that sigma lies between 0 and 1. Let's go a little further now. That's interesting. Probability of arrival Q is that we don't know what K is, but we're close. Let's get the probability that the Q size itself is of such a size n, given that the arrival Q's. And by the way, once I write that down, and if you go back to how I began this little section here, let's see, where is it now? I'm looking for the conditional distribution of Q size. Condition on what? Condition that you join a Q when you come. When you come in, how big is it? And notice I'm ready to solve that. Down here, I'm asking for what the probability Q size is n, given you have to Q. That's the conditional Q size distribution. So let's try to get this. That's what I was after. Okay. Well, that's equal to if we're going to use the conditional probability, we need the probability that the Q size is n, given the Q's, which means the Q is n, so how many does the arrival find? If the Q is size n, how many did that arrival find when it came in the system? N plus m. All m servers are busy to form a Q. How many in the Q? N. M in the servers, n in the Q. So that's R sub n plus m. That's the joint probability. Q size is n, given you have to Q. And downstairs, I basically have to put the probability of the condition itself, which is the probability of arrival Q's. So this is basically probability of A given B, just to remind you, is the probability of A and B over the probability of B. That's what I just did. So let's continue. So the probability that the queue size is n given that the arrival queues, I'm going to plug into the equation above, is equal to, what is r sub n plus m? It's k sigma to the n plus m over, what's the probability of arrival queues? I just put that 3 lines ago. It's k sigma to the m of 1 minus sigma. So finally, the probability that the queue size equals n, given the arrival queues, that's the conditional queue size distribution, is simply equal to 1 minus sigma, sigma to the n. And that's good for all n greater than or equal to 0. So let me identify that as something very worthwhile. I just found out what I set out to seek, namely the conditional queue size distribution. And let's not pass this quickly. I want to make a note. The conditional queue length, given a queue exists, is always geometric. Isn't that a geometric distribution? For any GMM system. That's a remarkable statement. We're able to pull out of our little monkeying around here a very general comment. Any GMM system, any one at all, has a conditional queue size which is geometric, and that number sigma is found by that functional equation on sigma. Okay. Okay, now that they're doing so well, let's go on. Let's go after the conditional distribution of waiting time. If you have to wait, how long do you wait? So let's now seek the conditional distribution of waiting time. Okay. So a customer who finds m plus n in the system, and remember, these are first come, first served systems. Don't forget that. Whenever I go after waiting time, I have to tell you what the order of service is. This other stuff didn't matter. You could have any order of service for the number. But now I want the waiting time, how long do I? So a customer, basically, who finds m plus n in the system must wait until in the queue, I'll say explicitly, in the queue, until, and I want to fill this in, so many customers, how many customers have to leave, okay, while he's waiting in the queue? There's m, and say a huge queue. So how many does he have to wait before he can get into a server? You get rid of all these guys, and one more, you have to make space for me in the m. So it's n plus 1, okay? Okay. Now this is the same, this is the sum of n plus 1 exponentials. How long is it? The sum of n plus 1 exponentials. Each at what rate? Excuse me? No, not mu. M mu. All the M servers are busy this whole time till they make space one. So the rate M mu. Close. Okay? So it's a sum of a bunch of exponentials. And if I take the transform, well, what is the sum of a bunch of anything that are independent? Convolution. These are all exponentials. Convolution of basically n plus 1 exponentials. And if I take the transform of that sum of that distribution, it's a product of each of those exponentials. So let me just point out the convolution for the sum goes to a product of transforms, if you will. So let's say that. That means that the waiting time density, the transform, well, what is that by definitions? That's the expected value of e to the minus s w. Remember, w is the waiting time. No conditions here yet, okay? But now I want to put a condition on. That's what this topic is, conditional distribution. So I want to talk about a related transform, w star of s given n, which is basically the expected value of this waiting time e to the minus sw, given the arrival queues and the queue size is n. Now, can somebody tell me what this is? I just told you upstairs what's going on with the convolution and the products. You got to wait for n plus 1 people to leave. They're leaving exponentially rated mu. The transform of the mu is basically mu over s plus mu to the n plus 1, okay? Yes? Well, this time, basically, this is not a, I'm taking n plus 1 exponentials, multiplying them, so it's mu over s plus mu to the n plus 1. That's the Laplace transform of a conditional distribution, okay? So w star of s given that the arrival queues, notice I'm getting rid of n now. I'm going to say for any n, okay? Just knowing that he has to queue, that's what I was really after, is equal to what I just cooked up, namely this w star of s given n, but I'm choosing n there. What's it probably have n? It's probably q equals n. And that q equals n given he must q. And over what range we're going to take this? From n equals 0 to infinity. So I'm just unconditioning on the number in q. That's all I'm doing here. So that's a sum from n equals 0 to infinity of, what's the probability q equals n given he must q? Well, there it is in the red equation. Just cook that up. That's why I cooked it up. So it's 1 minus sigma, sigma to the n. That's the condition. And what's a w star of Sn? I just did that at the top of the page. It's mu over s plus mu, all of that to the n plus 1. Well, can you do that? Again, it's a geometric. Take out the things that don't specifically depend upon n. And with your baby piece of algebra, you're going to get 1 minus sigma times mu over s plus mu minus mu sigma. Now, let's invert that, okay? I want the conditional waiting time given that the arrival has to Q. That's what I was after. Not its transform, I want its density. And that's equal to the inverse of this. And the inverse of that is very simply, that's constant 1 minus sigma times mu, e to the minus mu, 1 minus sigma y. Another lovely equation. So in words now, and then we'll finish, the conditional PDF, condition on your queuing, the conditional PDF of queuing time is exponentially distributed. Wow. You have to read that equation. Oh my God, that's an exponential, isn't it? Exponentially, let me clean this up. Exponentially distributed for all GMM. Just like with the conditional number. And I'm going to mark this with a 4-star because I think I've used the other 3 stars for something else. Okay, so we took a little side excursion to find these conditional number and waiting time, but we still have the problem of finding k and those first set of r's. No time to do that today, but guess what? We're going to do it Monday. Okay, so enjoy your weekend, and I'll see you then.